We'll go from current slide. And, okay. Now this first announcement, judging from my audience here, is probably not the most appropriate, but they have it, and I'm recording it, so if the others want to hear it, except maybe Jay, we'll see, okay? Are you the next Miss Lawson State? Okay? There are interest forums happening today and tomorrow, okay? Today it's going to be from 2 to 4 over in the Space Center in the new Academic Success Center on the Birmingham West Campus, but barely on the West Campus. It's just across Wilson Road on the west side of Wilson Road. Tomorrow it'll be on this campus from 11:30 until 1. We have an hour and a half here. They have 2 hours there. I don't know why. Okay? Building A, room 182, that's the testing room, I believe it is, if you remember where that is, on this campus. The requirements are currently enrolled at Lawson State Community College. You are. 3.0 cumulative grade point average. I think probably most of you are pretty close to that anyway. Completed or currently enrolled in a minimum of 16 credit hours at the 100 level or higher. And I think y'all all fit there too. And active in extracurricular activity or organization. Okay? If you want more information, you can contact Miss Leslie Harper. She's on the Birmingham West Campus. Miss Janine Jones is there. And Miss Kimberly Moore, though, is on our campus here. And her number here is 3420. Her office is right across from the testing room, next door to Miss Dr. Renee Herndon's office. So that's this one. Pass along to any of your friends who may be interested as well. Okay. And this is for those who are possibly thinking of transferring to Alabama State when they finish here. Today there is some type of an official signing ceremony with Alabama State University transfer memorandum of understanding. They'll sign the agreement this morning at 11:30 on the Birmingham West Campus, the Academic Success Center again. If you're able to attend, you certainly are welcome to go. The main thing is, if you're thinking of transferring there, we're going to have a formal situation in place that will probably make it easier to do so. So that's coming up this morning. Now, I also received the final exam schedule this morning. They sent it out last week. A bit late, but it's here. And I have not yet figured this out, okay? But they've moved the classes to start at 8:30, which most people seem to think was a good idea, but they still start final exams at 8. So I'm not certain why they do that, but they are doing it. But your final is going to be a take-home final, so you just have to have it back into it. Except for this, okay? Say this again.
Is our final just a test for chapter 4?
No, we'll see. I was thinking my other class. It may be. If we finish chapter 4 before then, which there's a chance, well, remote chance, but a chance we could, then we could actually have the final earlier, and then the final exam may be what we do. And there's one more chapter I'd love to get to, and spending this much time on the announcements probably is a good way to do it. Yes, but chapter 5, I would love to do some of chapter 5. Now, if we don't have time, but just for a little bit, then it will be 4 and 5, and that will be the final exam. If we finish 4 pretty quickly, which doesn't seem too likely, but it could happen, then what we cover in chapter 5 will be the final exam. Okay, just depends on how much time we have left and how much to get there. I'm going to change books next year. Same author has another book that is Early Transcendentals. and it incorporates logs, exponential, and other transcendental functions in with what we're doing. This book, because it doesn't say that in the title, they do that in a separate chapter. See, we would have already been exposed to differentiation of logarithms and exponentials. We haven't been, so now we're going to have to go back and pick it up. So anyway, going to try to do that with that. Let me get... Hey, you want it, right? Ayana. I'm not going to promise, but by the end of the term I'll get it right. No, I have no promises at all. Okay. Are you a Lawson student or are you a transient? I thought you were. Okay. I know that one, I believe it's Taylor, I believe, is, I think, actually a UAB or UA student. So that's why I was asking. If you're interested in Miss Lawson State, I have the information up here. Okay. There's an information session today and tomorrow. Today on Birmingham campus, tomorrow on this campus. So if you want information, there it is. I was just talking about the final exam schedule. But here is sort of a, let's see, did I answer your question? Okay, good. Several things happened there. Here is a one fly in the ointment about final exams and when they're scheduled and when they're due and that kind of stuff. Are any of you graduating this term, this spring term? Frank, you are. Okay. All right. Let me get Frank here. Okay. He's here already, but I've got you marked here. All right. Here's the problem with you, okay. Graduate grades are due in by Friday, May 4th. So whenever I get you your test, I think our last day of class is that Monday, which would be April whatever. 14, 22nd, maybe, whatever, the Monday the 22nd. That's our last day of class. You'll have to have yours in by Friday. The rest of you have until, I'd like to have them in before Wednesday of the following week, the 8th, because we have to have grades in by 12 noon, so I'd like to have them in sooner. So the times, they won't bother us any because they'll take on finals, you turn them in whenever you want to. But if any of you are taking any other classes, notice that if it is an 8 o'clock class, on either Monday, Wednesday, or, 8:30 class on either Monday, Wednesday, or Tuesday, Thursday, your final is going to be at 8 o'clock, either on a Monday or a Wednesday. Okay, so you'll just have to be aware of that. Okay. Or Tuesday, Thursday, either one. Monday, Wednesday, or Tuesday, Thursday, your final is going to be at 8 o'clock. Okay. Even if you have an 8:30 class. Weird, but true. Okay. Any other questions? All right. 2, 7, 7. Okay. And Frank, if you're interested in this Lawson State, I've got the information up there. Okay. All right. Okay. Thanks. Okay. Now, we're in any questions math-wise or otherwise? All right. We're almost through with 4.2. Okay. However, the slide is not shown in 4.2, so I've gone on to 4.3, and let's see if I can find a lot of white space. Probably that's going to be my best bet right there, okay, to do example 7 and example 8. Neither one of those are on the slide set, but they are in your book. So let's do that. Example 7. Find the area of the region bounded by the graph of f of y is equal to y squared. Let me get my pen set up. Okay, f of y is equal to y squared, and the y-axis, now I'm going to write it like they say, y-axis, I can't write, that is where x is equal to 0. That defines the y-axis, where x is equal to 0. Okay? For the region 0, on the interval 0 less than or equal to y less than or equal to 1. Okay? Now, what we have here is this situation. This is a pretty ugly rendition of the graph here. Okay? You basically have, that is the graph of f of y is equal to y squared. Now that's obviously not a function if you include the bottom half. So I'm going to take the bottom half off, but it's a parabola on its side like that. But it's only the upper half, because if it were the lower half, that wouldn't be a function. I mean, if it was included the lower half. Now it could have been just the lower half without the upper half too, but we've defined it from 0 less than or equal to y less than or equal to 1, which leads to put those points on here. If this is 1 here, this is 1 here, there's the point. So we're just looking at this portion right here. Okay? Now, if the function is defined from 0 to 1, and it's always defined in y, then it's a lot better approach to get Frederick here, okay? And I did the announcements earlier. If you're interested in Miss Lawson State, I've got information here. Becoming Miss Lawson State. Never mind. Okay. Okay. You'll have to fight with Jake on that one. Okay. All right. But if your function's defined in terms of y, your limits are in terms of y, it's a lot better generally to choose delta y's rather than delta x's. And that's what they show you in the text. I wish the graph were here. You wouldn't have to look at my ugly one. But you do your delta y's like this and make your little triangles like that. Okay? However you do the triangles, whether they're circumscribed or inscribed, however you do it, you do your little triangles that way. Okay? Now, remember we're still doing the deltas here. Okay? And how we do that, if you think about it, the length now is the y value. The x value. We've got everything turned around. So this is equal to x, right? F of y is equal to x, just like f of x is equal, f of y is equal to x, just like f of x equal y. Okay? So the length here is your x value, which is y squared. Okay? Now, because we're doing an interval on y, your delta y is now b minus a, which is 1 minus 0, divided by n, right? Number of intervals that we have. So this would be 1 over n. That's your delta y. Now, what values of y do you have? The first one, they're counting, I equal 1 to n. So your summation, which is your area, I want to make sure they use the same word. The area is the summation of your y value, okay, which is, okay, there's the, okay, let me put it in the same order they do. The f of CI, they call it, okay. I was trying to remember which terminology they use, times your delta y, okay, where C is some value of y. Now, what value of y is the C, okay? Well, it's either going to start at 0 or start at 0 plus delta y, okay? That will be the first value. And they're using the using the values here of your each of the i's here would then be, it's going from 0 to 1, so it's going to be I squared, okay, I over n squared, because the length of this is, the width is delta I, which is that. The length is 0 plus delta I, okay, so the first one is going to be 1 over n. But you got to square that because that is your y value. And then the next is going to be the next I over n. Okay, so basically your length here is going to be I over n. This length here is going to be your I over n. Okay? Because each one of those is going from the next I to n. I is equal 1, 2, 3, 4, 5 divided by n. Okay, so whatever that is, and so your length is going to be that squared. Okay, so your summation, this is going to be your FC sub I, is I over n, because each one of these is the next I up divided by n, because your 0 plus whatever your ith is over n. Okay, that's what you're dealing with. So there's your area, and this is going to be the summation of I squared over n squared times 1 over n. Okay, now I forgot to do this. I is equal to 1 to n. Okay, I is equal to 1 to n. Well, the n has not being counted. It's not going up. It's a fixed thing, whatever you decide that n is going to be. So let's pull that out. You have n squared here and n cubed there, so it's 1 over n cubed times the summation of I squared. Okay? Now, summation of I squared, if you remember, and if you need to, turn back to the table at the top of the page. I don't recommend you memorize this. Look them up when you need it. Way back now. The theorem 4.2 on page 259, the summation of I squared is n times n plus 1 times 2n plus 1 divided by 6. Exactly what we've got here. So this is going to be 1 over n cubed, and this is going to be n times n plus 1 times 2n plus 1, all divided by 6. That's what your summation of I squared is. Okay. Now, magically, they come up with a set of numbers here. Here's how they did the magic. Let's multiply these two together, and what does that give you? 2n squared plus 2n plus n plus 3n plus 1. Okay? And then multiply that by n, and that makes qn cubed plus 3n squared plus 1n, or just n. Okay? And that's divided by 6. Okay? So let's take that and divide by this. Okay? Well, you have 2 over 6. That's n, well, that's just 1 over 3. Okay? Because that's your n cubed over n cubed, and 2 divided by 6, 1 over 3. Okay. The next term plus, well, the 3 will go into 6 twice, so it's 1 over 2n, because n squared will go into n cubed n times, and the last term is just n over n cubed, so that would be n over 6, I'm sorry, 1 over 6 n squared. Okay, so when you divide this by the 1 over n cubed, I know it's ugly. The deal here is, as n is going to infinity, both of them goes to 0, so you're left with 1/3. So the sum of that would be 1/3. Okay. Now I wish I had left the PowerPoints up. We talked about the midpoint rule last time. It says approximately an area with the midpoint rule. Oh boy, what a pain in the neck this is. What makes it difficult is having to come up with those midpoints. Okay? And it's so much easier just to do it. Well, I guess it doesn't make too much difference. I don't want to go back and re-show the, I'd have to get out of this slide set and go to the previous one to show that. But it's pretty straightforward here. It's given in the text. Hopefully you've got it. You first have to identify these 4 midpoints because they did n's equal to 4. Thank you for being that small a number. Okay, so your delta x is in, and your, what it is, use the midpoint rule with n equal 4 to approximate the area of the region bounded by the graph of f of x equals sine x and the x-axis for x between 0 and pi. Which is a good thing to choose because 0 to pi, sine is like this. Okay? If you started doing anything past pi or before 0, you got on the negative range. So you basically almost have to be that. So that's going to be your thing. You're going to do it from 0 to pi. So there's your b minus a is pi divided by 4. So pi fourths is your interval. Okay? Now, and what you're doing, if you evaluate sine at each of those intervals, then C1 would be half of pi fourths, so that would be at pi eighths, 3/8 pi, 5/8 pi, and 7/8 pi. That would be the midpoint of those intervals. If you split the intervals, I'll kind of write it out here for you. I know it's a lot of arm waving. If this is your graph from 0 to pi, okay, and you're doing 4 intervals, it'll be pi halves, pi quarters, 3/4 pi. Okay, your b minus a over n would be pi minus 0 over 4, which would be pi fourths. Okay, then your midpoint of each of these will be pi eighths. This is pi fourths here. This is pi halves, 3/4 pi, and pi. Okay, the midpoint then, the C1 would be pi eighths. C2, the midpoint would be 3/8 pi. C3 would be 5/8 pi. And C4 would be 7/8 pi. 7 pi over 8. Okay. And then you would do your area then of, I'll sort of draw it for you. Okay, there's the first one. There's the second one. Oops. Did I write? No, I had it right the first time. There's the third one, and here's the fourth one. Okay, sort of like that. Okay, those are your approximate. Now, why is this any better? Well, if you were doing inscribed, you're always too small. Circumscribed is always too big. Okay, if you do the midpoint, then you undershoot here by about the same much you overshoot here, and the same things here and here, if you had a better picture, and there. Not exact, but it just gives you a better estimate. And then what you're doing your, remember your delta x is this, pi fourths, so you would have your function, which would be sine of x, evaluated at each of these places, the summation, times your delta x. Okay, that's what, and this would be in I equal 1 to 4, because that's what we chose, n's equal 4, and these are x, they call them c sub I, but then the delta x. Okay, so that would be the sine of pi eighths plus the sine of 3/8 pi plus the sine of 5/8 pi plus the sine of 7/8 pi. Add those together, divide by, or multiply by pi fourths. That's your delta x. That's your summation. Because the delta pi over 4 can come on the outside. There's no I dependence in there. So you just sum those up. If any of you have a calculator, you can do it real quickly. Sine of pi 8's not one of our favorites, so you have to do it actually on a calculator. Anyone got it? Plus sine of 3/8 pi, plus sine of 5/8 pi, plus sine of 7/8 pi, and then you multiply, you add those together, those sides together, and then multiply by pi over 4. And it should give you fairly close to, anyone get it? Anybody? Sine of pi 8 plus sine of 3/8 pi plus sine of 5/8 pi plus sine of 7/8 pi. Those are the heights. The widths are always delta or pi fourths. So add those together, multiply by pi fourths, what do you get? Sine of pi 8 plus sine of 3/8 pi plus sine of 5/8 pi plus sine of 7/8 pi. Add those together and multiply the answer by pi fourths.
Sine of pi plus sine of 3 pi plus what?
Sine of pi 8 plus sine of 3/8 pi plus sine of 5/8 pi plus sine of 7/8 pi. Add them together and multiply the answer by pi fourths. Pretty slow calculators, huh? Say it again.
0.023.
Ooh.
I got 0.109.
Oh boy. Are you in radian mode? Ah, that may be the problem. Be sure you're in radian mode if you're using these kind of angles. Say that again.
After you add them all, divide them by what?
Then you multiply it by pi fourths.
I got 2.61.
Okay. 2.052. That's what they have in the book. 2.052. Okay. Did you multiply by, yeah, pi fourths? That probably was what you need. Multiply by pi fourths. And now, without telling you how, we know the answer is 2. Not bad. Not bad at all. Okay? That's like less than 3% error. Okay? The answer is actually 2. But we don't know that yet. We will later. All right. That finally finishes 4.2. Again, let me give you the homework exercise. Any question on that? Sorry, I didn't. Sort of, without having to pull back up how we got the midpoint, that's exactly what we did. You do the intervals and then pick the midpoint, and that's where you evaluate your function. Okay, homework exercises here, 5 through 9, they're all at Calc Chat. 5's at Calc View. 11 through 15, they're all at Calc Chat. 17 to 23, they're all at Calc Chat. 21's at Calc View. 25 or 27, both at Calc Chat. 25's at Calc View. Any of the odds, 29 to 33, all at Calc Chat. 33's at Calc View. Do 35, it's a Calc Chat. 37 or 39, they're both at Calc Chat. 39's at Calc View. Any of either 41 or 43, both at Calc Chat. 43's at Calc View. 45 should be at Calc Chat. Any of the odds 47 to 55, all at Calc Chat. 49 is at Calc View. 57 to 61, all at Calc Chat. 57 is at Calc View. 63 and or 65, they're at Calc Chat. 65 is at Calc View. You can explore the concepts 67 and or 69. We finally did the midpoint rule. You can do that now. If you want, they should be at Calc Chat. 71 should be at Calc Chat. 73 is a true-false. It should be at Calc Chat. 75 is a writing type problem. You can think through that or whatever you want to do with that. 77 is a seating capacity problem. You can take a look at that if you'd like. And then, of course, the Putnam challenges are exactly, completely up to you. All right, any questions? All right, let's back up then. We're continuing Chapter 4, which is integration. 4.3 is Riemann sums and definite integrals. And if you haven't figured it out yet, what we've been doing is pretty close to what a Riemann sum. Well, a few minor details in it, but that's pretty much it. Oh, but we haven't done definite integrals yet. We're going to get there. Okay? The objectives here are to understand the definition of a Riemann sum. We'll evaluate a definite integral using limits and geometric formulas. That sounds like fun. And then we'll evaluate a definite integral using properties of definite integrals. That sounds like even more fun. Okay? So we'll start with Riemann sums. And by the way, and this is time for my paid commercial announcement here. This, of course, my best class ever. And how many research papers have I got in so far? Uno! Okay, 1. And we have, what, 3 weeks left in the term? If that? Okay, folks, please get that means 3 weekends to work on your paper. Please get them in sooner rather than later. Okay? Which also means, Test 1, this class is really good about getting the test in. 2 people, just 2 people, have not turned in the first test. Okay? Test 2, 4, 5, 6, 7, 8 of the 14 have turned in test 2, so 6 of you haven't turned in test 2, and test 3, uno again. Okay, it's turned in test 3. Please be working on those. Get them in sooner rather than later. Okay. So, what I was going to say before I got off a little bit is who in the world was Riemann? Okay? We're going to see his picture a little bit later, or at least in the book you will. That's who the sums were named after. He would be a potential paper topic, either stuff about him or how did he develop these Riemann sums? Why did he develop the Riemann sums? Any of those would be decent topics as well. But let's do first example 1. Consider the region bounded by the graph of f of x is equal to the square root of x. Now, if that's beginning to look a little familiar, that's exactly what we were looking at before, except we were looking at the area here going this way rather than the area underneath here, because these are pretty much equivalent expressions here. Square root of x and the x-axis between x equal between 0 and 1. X between 0 and 1. This time we're doing our limit as n approaches infinity of the summation for I is equal to 1 to n of L of C sub I times delta x sub I. That's what we've been doing before, right? For C sub I, they say now is the right-hand endpoint, okay? Doesn't matter where, okay? Of a partition, and this partition is given, ew, why would they do this? This is where the subtle, or not so subtle differences come in, okay? This C sub I is not I over n, like you would expect. For some reason, they chose I squared over n squared. And delta of x of I is the width of the ith interval. Okay? Well, the width here is a variable width. This first one's tiny. The next one's fairly small. The next one's bigger, and really big. Why in the world would they do that? It doesn't really matter why they did it. Okay? The intervals do not have equal widths, which is a real shame, isn't it? Okay? And we've got to figure out what our sums are here. Well, frankly, this doesn't seem like it's, well, yeah, it might be happening a little bit. because where the function is changing most rapidly here, that's where you have your smallest interval, so you have less error then. Where it's changing more slowly, though not quite slowly enough, are the bigger intervals. You're still overshooting because the right-hand end is in an increasing function is going to always be overshooting. Okay? So there is your the delta x being the width of that interval, which is not equal widths. So that is a problem. So the width of the ith interval is I squared over n squared. Okay? Because they just told us the c sub I was that, so I squared over n squared is the width of that. Well, oh, I'm sorry. I squared over n squared is c. And then you're going to add a delta x to that, okay? And so the delta x of I will be the next x of I, which is I squared over n squared, minus the previous one, which is I minus 1 squared over n squared. That's now your new delta x of I. Boy, what a pain. Okay? Now, are they going to carry forth the yes? All right, let's see how they do this. Okay? They do I squared over n squared minus, now you got to square that binomial. That's not too bad, is it? I squared, square the binomial. I did the first one. Next. Hint, it's a minus. Square the binomial. It's not that hard. It's 2i, remember, plus 1 over n squared. Okay. Now what we did there, you square the first, twice the product, square the last. That makes these two positive, but that one a negative. Because of the negative there. So if you work this out, this will be I squared, they're both over n squared, minus I squared, so the I squareds go away. Gone. Plus 2i, because minus and minus is plus, minus 1 over n squared. There's your delta x sub I now. Why would you do this? I don't know. Okay. Now, and I think that's what they show. Oh, okay, they show one more step. But this is what they get. 2i minus 1 over n squared. Okay? They did the same thing I did. They just did. I thought they skipped a step. Okay? Now, that's the width of the ith interval. Okay? Now, so the limit is, that's your delta x, this thing, and your f of c of x is the square root of, and remember, since you're starting at 0, the value is going to be I over n, but that's your delta x, but this delta x is I squared over n squared, so you're stepping that up each time. So it's the square root of I squared over n squared. Which, for one thing, shows you why they chose such a weird interval. Because this is now an easy thing to calculate. It's just I over n, right? Square root of I squared over n squared is just I over n. Okay? So hopefully they'll do that here. Okay, and they did several steps there at once. So it's I over n here, and then you have an n squared here, so you have a 1 over n cubed there, and then you have an I from here, of the square root of I squared is I, multiplied by that. Okay. So it's the limit n going to infinity of 1 over n cubed times the summation from I equal 1 to n of 2i squared minus I, which is the I from here times this is 2i squared minus I. So that's where they got that part. Go back to your favorite little formulas there and that would be the limit of 1 over, and why in the world don't they take the 1 over n cubed out for I? I'm not too sure. No, it's okay. Leave it there. I think I know why. Okay, so it's 2 times your I squared. This is our I squared from before, minus I, which this was your I from that table back before. Look these things up. You'll have your open book when you're doing the test. You know, these are, in my mind, not worth memorizing. But if you want to, go ahead and knock yourself out. So what do we have here? That's the limit as n approaches infinity of 1 over n cubed. Okay, now let's multiply these things out. Remember what we had before? This was 2n squared plus 3n plus 1 times n would be 2n cubed plus n squared plus n over 6. Okay, and then this is an n squared plus n, only it's a minus n squared minus n over 2. All right. Is there some way to make this a little easier? 2 times that would be 4n cubed plus 6n squared plus 2n over 6 minus n squared minus n I'm going to put them both over 2 just to make it maybe just a little bit easier. Maybe not. Okay. This will be a 3 here and a 2 there. 1, so this will be over 3. This will be over 1, and this will be over 3 there. Okay. Let's see. That will be the limit as n goes to infinity of 1 over n cubed. Okay, let's see what we can do with this. 2/3 n cubed, and here we have a plus n squared minus n squared over 2, so that'll be a plus n squared over 2. It really doesn't matter what these turn out to be, but we'll go on and carry it through. And this will be a plus n over 3 minus n over 2. I think that's minus n over 6. Not that that really matters that much, because when you divide by n cubed, you're going to have a 2/3 here, and you'll have an n down here, and you'll have an n squared down here, and the limit as n goes to infinity will go have those terms going to 0. So we wind up with 2/3 as our answer, and that's what we got in the book. Okay, I hope I wasn't skipping too many steps for you, but if it didn't feel right, remember I said what we're doing with the area under here, whereas the previous example was doing the area up here. Well, here we have a block of 1 by 1, so the area under that is 1, right? And this, if you remember, was 1/3. This is 2/3. So we could have done it just like that. But that would have taken all the fun out of it, right? Yes, okay. We want all the fun that we can get. So, sure enough, our did that. Okay, I got to erase. Oh no, we did that. But here I've got to erase this because it's now too messy to read. And that gave us, okay, they've combined the like terms here, I guess. Yeah. Other way to do this is multiply this by 3 over 3, which will make this 6 here. That'll be 3n squared minus 3n. Yeah, minus 3n. So it'll be 2n squared over 6 minus 3. Oh, 4. Okay, I lost it. 4n cubed over 6 minus n squared. No, had it right the first time. 4n cubed over 6, that's that part, plus 3n squared here. I think they, oh no, they kept it over 6. Ah, yeah. Here we wound up with a 3n, I'm sorry, 3n times n, 3n squared times 2 would be 6n squared minus that, yeah, 3n squared, that we got it right. And then, but again, these out here really don't matter, but you do get a minus n left over here, okay? These are going to go away. This is the only one that gives you anything, and that gives you 4 over 6, which is 2 over 3, okay? And they did the step here for you. 2/3 plus 1 over 2n minus 1 over 6n squared. Exactly like we got at limit as n approaches infinity, the last two disappear, leaving is 2/3. Okay. Now, we know that the region shown before was the area of 1/3, that's what I said, and then the area here has to be 2/3 because this is a 1 by 1 square, which is an area of 1. Because the square bounded by that and that have an area of 1, you can conclude that the area of the region has an area of 2/3. I think we've said that 3 different ways now. Okay. This agrees with the limit found in example 1, even though that example used a partition having subintervals of unequal width. Okay, the one we just did. The reason for this particular partition gave the proper area is that as n increases, the width of the largest subinterval approaches 0. Okay. That's a weird kind of statement here. Basically what they're saying is this, that even though your subintervals are getting larger and larger and larger as you go out here, as long as you let the n get larger and larger and larger, even the largest subinterval is approaching 0. Okay? It's got to be. Okay? So, therefore, you can still do it. Even though it doesn't look fair, it looks like you're introducing more error, doesn't matter as n goes to infinity, you're approaching 0. That was sort of a weird statement, but it is true. This is a key feature of the development of definite integrals, okay? That no matter what your partition is, it doesn't even have to be regular like that, though it was a strange regularity. It could be anything as long as that maximum interval is approaching 0 as n gets very large, which of course it has no choice but to do, then that works. So in the definition of Riemann sum below, note that the function f has no restrictions other than being defined on the interval a to b. You don't have to define any particular delta x. Okay? The f be defined on a closed interval a to b. That's all. Defined. And delta be a partition of a to b given by a is equal to your first partition, a sub 0, and that's got to be less than x sub 0, less than x of 1, less than x of 2, less than x of 3, all the way up to less than x of n minus 1, less than x of n, but x of n is going to be your b. So that's your subinterval. It doesn't matter where you put the intervals and how big or how small they are, that's what they are. The delta x of I is the width of the ith subinterval, which goes from x of I minus 1 to x of I. That's all you need. That's your delta x. And they can be varied. If C sub I is any point in the ith subinterval, it could be an endpoint, or it could be a midpoint, or it could be any point in between. Okay? Then the summation from I is equal 1 to n of f sub C sub I, so delta x of I, where delta of x of I has to be, C sub I could be the left endpoint, the right endpoint, or any endpoint, or any point in between. That is called a Riemann sum of f on the partition delta. Okay. So delta, which used to be difference in, now means a partition. Any old partition you happen to have. Okay? So we've taken out what the definition of delta x is. It's just this now. Delta x of I can vary from interval to interval. Okay, subinterval to subinterval. It doesn't really matter. Doesn't even have to have a rule that ties them together. Okay? Now, the width of the largest subinterval of the partition is called the norm. Now, that's not usually the same definition we have for the term norm. That usually means taken to 1. Make sure we weren't running out of time because I was running out of students here. Huh?
You said 40 minutes.
Yeah, I know. I was thinking losing students like crazy here. Okay. The norm is denoted by the rather bizarre notation here. Delta is a partition. In vectors, this would be the magnitude of a vector, those double lines. Not quite the same thing, but it has sort of the same meaning. It's the size or the width of the largest of your partitions. Okay? And that's the norm. If every subinterval is of equal width, the partition is regular, and the norm is noted just like we did before, b minus a over n. Okay? But if it's not, the norm is still the largest place. That's a regular partition. Now they're all the same size, so that's the maximum is the same. Okay. For a general partition, the norm is related to the number of subintervals in A to B in the following way. B minus A over the maximum of these is always less than or equal to n. Okay? So this is actually going to be something less because this is the biggest one. Okay? The average one would be pretty close to what n would be. And if these are all the same size, this is exactly n. Notice all they've done here is flipped the multiplied by n and divided by delta n. So that gives you that if it's regular. If it's in general, this is exactly it. See, if it was regular, this would be an equal sign. If it's anything else would this be the maximum, then this is going to be less than or equal to n. Okay. So the number of subintervals in a partition approaches infinity as the norm of the partition approaches 0. Because no matter how big that norm was, it's the biggest one you got, but as it approaches infinity, it has no chance but to be approaching 0. Okay? The converse of the statement is not true. That statement there, just because the norm is approaching, that the n approaching infinity does not imply, let's see, what have we got going here? Yeah, okay. From 0 to 1, the partition just before 1 is 1/2. Just before that is 1/4 and 1/8, 1/16, and you go down. But guess what? You're getting closer and closer to 0, but never reaching there. But this n is going to infinity, but still your norm is 1/2. So that means the norm does not always approach 0 as n approaches infinity. The norm is approaching as the number of subintervals approaches infinity, as the norm of the partition approaches 0. So the norm of the position is approaching 0, that implies that. It doesn't mean the other way, because this norm would always be 1/2. That's not approaching 0, it's 1/2. So just because the n is approaching infinity doesn't always mean the norm is going to 0. Even though I said it sort of would have been, okay. If you had a weird partition like that. Okay. Where is figure 420? Oh, there it is. There, oh, there it is, right here. This one. Okay. As shown in Figure 420, for any positive value of n, the norm of this partition is 1/2. Okay, because that's there, it's fixed. Now, the partitions are getting smaller, smaller, smaller as you get close to here, but that's not. Okay, as n is going to infinity, this is still your norm. So the norm is 1/2, and that n does not approach, as n approaches infinity, does not imply that this is going to 0, because it's fixed at 1/2. Never is going to approach 0. Okay. So sorry about that. I said it a little backwards earlier. Through with that. Let's move on to definite integrals. To define a definite integral, consider the limit as the norm is approaches infinity, is approaching 0. That maximum interval is guaranteed to be going closer and closer to 0. Then the summation of that I equal 1 to n of alpha c sub I delta n is going to have a limit. Okay? Let's say it has that limit. That's the limit L. To say that this limit exists means there exists a real number L such that, does this sound familiar? For any epsilon greater than 0, there exists a delta greater than 0 such that for every partition, as long as that delta x is less than this, the norm is less than delta. Now, see, this is a capital delta, that's a lowercase delta. They don't look anything alike, do they? But that just happens to be the choice of Greek letters here. It follows that if you, for any epsilon greater than 0, you can find a delta also greater than 0, such that as long as this norm is less than that delta, you can guarantee that the difference between the limit and the summation, that is the limit 4, is going to be less than that. Regardless of your choice of C sub I, whether it's left hand, right hand, center, or anything else in the I subinterval of each partition. Okay? The wording is just like our wording for the formal definition of a derivative, only there you're letting your delta x go to 0, and you go here. This time, your norm is approaching 0, and as you can, for any epsilon greater than 0, you can find a delta also greater than 0. You might have to get pretty small, such that this difference is going to be less than epsilon anytime the norm is less than delta. Okay? Regardless of what you choose. So, here's the definition of an indefinite interval. If f is defined on the closed interval a to b, now notice that all it takes is it to be defined. It doesn't say it has to be continuous. It doesn't have to say it's differentiable or anything else. Just defined on an interval a to b. What does that mean? There aren't any places it's going to infinity. Okay? It has to be defined everywhere on the interval. And the limit of the Riemann sums over the partition is defined over the closed interval, and the limit of Riemann sums over that, as long as your norm is approaching 0, that is what your limit is. Okay? That this limit does exist, as described above, then f is said to be integrable on this interval a to b. Now, I get tongue-tied when I'm saying integrable on the interval. Okay, they just sound too much alike. So if I say it wrong sometime, you understand what I'm trying to say. And the limit is denoted by, the limit is this del, the norm is approaching 0 of this thing here. Notice what's happening here. This summation is stretching into a script s rather than a angular s. This is script s, really stretched out. And your f of c becomes your f of x, your delta x becomes your dx. Just like the delta x before in a derivative became a dx then. Okay, this becomes that. Now, seems like, oh, okay. These are the limits of the interval that you're taking the integral over a to b. The limit is called the definite integral from a to b of f from a to b. The number a is the lower limit of integration, and the number b is the upper limit. Yes?
Test 3. I misplaced my test 3. Do you have an extra copy?
Let me see if I do. I don't know that I do, but let me check. Okay, I'm getting warmer. I'm not going to take my shirt off. Okay. Oh, and by the way, I do seem to have one. Now, that probably means somebody hasn't come by to pick it up. So that's just their problem. No, I mean, I'll make another copy if I need it. Now, what I forgot to give y'all is graph paper, and this did have a graph on it. I know people who have turned it in. Do you have graph paper, or do you need some? You got it. Okay.
Thank you very much.
All right. Now, something I want you to note here. Though you can do it the other way, A needs, of course, to be, by this definition, less than B. It needs to be that way, right? You go back to your partition, your x of 0 was your A and your x of n was your B, and they had to have all those less than signs in between, okay? So A needs to be less than B, okay? If it ever isn't, and you'll see this in a minute, then you just negate it, okay? But don't worry about that now, but for now, that's why they say upper limit and lower limit. Upper limit is the larger number, lower limit is the smaller number. Okay. The Riemann sums are defined for functions with very few restrictions. A sufficient condition for a function f to be integral on a to b is that it is continuous. Yes, now we get our continuity in there. That will guarantee that it's defined if it's continuous, okay, on a to b. So the continuity implies integrability, okay, on a word. If a function f is continuous on a closed interval a to b, then guaranteed it is going to be integrable on a to b. That is, integral from a to b of f of x dx exists if f of x is continuous from a to b. Okay. It may exist if it's not continuous, but it's guaranteed to exist if it is, which is good to know. So, now they haven't brought this to mind yet, but this notation is antiderivative, okay? We're doing the antiderivative. We know how to do it. We did it way back before, remember? But we didn't have limits on it before. So what? Seems like they haven't defined it yet. Oh, I see. Don't tell me they want you to do all that. Oh, my word. Yes, they do, don't they? Okay.
Just solve it and then plug in the values and add them together.
That's exactly what I want to do, but they haven't told us that's the rule for doing definite integrals yet. That's why I said, wait, they haven't gotten there yet. But you see, you're just saying the fundamental theorem of calculus, part 1, okay? That's where I want to be too, but they're having you do this awful mess here, okay? I wish, this is just like doing differentiation using the limit formula. Yeah, not the way to go. Okay. Okay. Number 1, that's a continuous function. 2x is a nice polynomial function, linear function, continuous from negative 1/2 to 1. I mean, negative 2 to 1. Okay? All right, and they're still doing subintervals. So, your B here is 1, your A is minus 2, so your delta X is equal to 1 minus a negative 2 divided by N. B minus A over N, which is 3 over N. Okay. Now, they choose the C sub I to be the right-hand endpoint. Okay. You could have chosen anything here. But now, if you think back, the last several we've done have always started at 0, right? And then we just did our function based on that, and it was really easy. This one's starting at negative 2. Okay. Now, the other thing that they're introducing here, and they seem to just be going right by it with no problem at all, is okay. Okay. You're starting down here and going up to here. Okay, that's the thing. Now, what they haven't defined for you is this is the area here, that's the area there. Okay? Before, we always had the function being greater than 0. In other words, this was always on top. We don't have that anymore, so they're kind of spewing all over that, but telling you this is what you want to get. Okay, this is going to turn out being a negative area because it's below here, and that's a positive area there. But yet they're not telling you anything about that yet. Okay. Now, what are your C sub i's? They start at minus 2 plus I over n. Okay? I'm sorry, 3I over n, because that's your delta x is 3I. So for every I, you're just adding one more 3 over n to it. Okay? So those are your C sub i's. And that's where you're evaluating your 2x. So this thing here, integral from minus 2 to 1, usually when I go to writing integral signs, I don't go back and do the limits, but that's what they're having us do, of 2x dx is equal to the limit as n approaches infinity of your summation from I is equal to, I guess they're still doing 1 to n, aren't they? No reason to change that, right? Of f of C sub I times your delta x sub I. Okay. And delta x sub I is always this. Okay. Just choose that. Okay, so this is the limit as n is approaching infinity of, and let's just go on and pull the 3 over n out. That's your delta x of I. That doesn't depend on I at all. And your f sub x is then going to be the summation. Let's go on and pull the 2 out too. We're not going to need that. So this 2 from here is going to come on the outside here as well. Okay, and this is I equal 1 to n, okay, of this is your f sub c of that, so this would be, I already pulled the 2 out, and that would be your minus 2 plus let's do it minus 2n plus 3I over n. Just, I think that makes it a little bit easier to do, times your delta x, which is your 3 over n. Okay. So what we have here is the limit as n approaches infinity of 6 over n. Now, I think I regret doing what I just did. We could have just left that minus 2 there. Because you see, that doesn't depend on this at all. So let's pull this out. This is just a constant. That'll just be minus 2. So I'll change that back. I didn't want to do that anyway. Minus 2 plus 3i over n. We'll do it that way. Okay. Now, if you go back to your table, I keep sending you back there because I don't encourage memorizing the things because I don't do them myself. But if you'll show there, a constant is just c times n. So this is going to be negative 2 times n plus, and then you have the 3 over n times, and the I is just n times n plus 1 over 2. Okay. Have enough grouping symbols there? Alright, so this will be the first part there is just going to be a minus 12 because the n's are going to cancel out for those parts. So you start with a minus 12 plus, and then the limit, I'll write this in, limit as n approaches infinity of, that would be 18 over n squared times n squared plus n over 2. Well, the 2 will go into 18 9 times. Okay? And then this will be, think about that. I just wish I had more room. I'm going to get rid of some of my graph here. Okay. Okay, let's leave part of that there. Hopefully I can write it all in here. You have a minus 12 from there plus the limit as n approaches infinity of I can hardly read my writing here. 9 times 1 plus n 1 over n. Okay, so that would be plus 9. So that gives us a minus 3. Okay. Whew. What a mess to have to do it this way. But see, this wound up being, and then you'll say, why didn't we do this the first time? There was a reason you had to slug through all this. This is a rectangle of dimension 2 by 4. That's 8, but it's half of that. So it's a negative 4. And this is a 2 by 1, which is 2. Well, I thought I had it down. And half of that is 1. And minus 4 plus 1 is minus 3. You say, well, why didn't we do that in the first place? Why do we have to go through all this? Because I wanted you to slug through those limits one more time. Okay? But it gives you minus 3. This confirms that it's a minus 3. Okay? Now, let's see. Okay. Let's watch them do it. That'll be a lot neater and maybe more organized than I was. But let's see. The function f of x equal 2x is integrable on the interval from negative 2 to 1 because it's continuous on the interval from negative 2 to 1. 2x is continuous everywhere. Moreover, the definition of integrability implies that any partition whose norm approaches 0 can be used to determine the limit. So we'll take the regular one, which is define your partition by subdividing -2 to 1 into some intervals with equal width, and that would be b minus a, 1 minus a minus 2, which is 3, divided by n. Okay? There's your delta x. Choosing a c sub I as the right-hand endpoint, that's what we happen to do. It starts off at -2, and then you add to it plus 3i over n. Okay? Because that's your delta x times your I. Delta x going up there times your I. You add that for every I. A plus I times delta x. Okay? And then we're going to evaluate that. Your integral will be from -2, blah, blah. So much easier when we do it. Your limit as your partition is approaching 0. I guess I was still saying n is approaching infinity, which you really need to say partition approaching 0. Of summation of I equal 1 to n, L sub c sub I delta x sub I, which will be, limit. Now they do it, n approaches infinity of L sub c sub I. So everything's the same here. So I didn't need to do it. I didn't need to apologize for doing it. Now your function L sub c is -2 plus that. Okay, that's your L sub c sub I is 2 times this. C sub I is this. 2 times that is this, and your delta x is that. So notice here, you can pull out a 1 over n squared. I'll leave it here. That's fine. But this is going to be a minus, well, I might get too carried away here. Let's carry it up. Okay. They're going to pull out the 6 over n. Okay. The 2 from here, the 3 from there, the n from there, all that comes out because that doesn't depend on I. So that 2 is out, 3 over n is out. And that just gives you this. Well, that summation, as we just said, is -2 times the summation of 1. We didn't really say that, but that's how they did it. Plus 3 over n. And again, that 3 over n can come out, and that's just the summation of I. Well, what does that give you? The limit is 6 over n, that's still in there. This is -2 times n, plus 3 over n times n times n plus 1 over 2. That is your summation of I. All right. Easy way to do this is -2n. These two n's cancel each other out, and that would be plus 3n plus, plus 3 halves n plus 3 halves. -2n plus 3 halves n plus 2n. And hopefully if you do that, boy, did they ever skip some steps here. Okay. All right, let's get it. Hopefully this will make it a little, may or may not make it clear. Let's get rid of those ends right off the top. Okay? Now, if you're combining this is -2n plus 3 halves of n plus 1. So that's 3 halves n plus 3 halves. -2n plus 3 halves n is 1/2 n. Okay. Oh yeah, okay. All right. Okay. Plus 3 halves. Okay. Let me write this out here. 6 over n times a minus n over 2 plus 3 over 2. Okay. This will be a 3 then. Okay. And this will be man. Okay. We're approaching it so differently here. So this will be a minus 3 plus 9 over n. Yeah, and that's exactly what they've got. Okay. I don't know. I'm sure there's a way to figure out. Yeah, I see what they did. This gives you some minus 12 over n, but they... Oh, okay. They got rid of these ends here. I see what they've done now. But we got minus 3. Okay. And that gave us minus 3. Okay. Because the definite integral in example 2 is negative, does not represent the area of a region. Because areas are by definition positive. They're not negative. Is it almost time? Well, close, but not quite. Definite integrals can be positive, negative, or 0. Okay, so this doesn't represent an area. This represents negative of one area added to the positive of another, negative area, whatever that. Okay, so for a definite integral to be interpreted as an area, the function f must be continuous and non-negative on a and b. Finally, they get around to saying, everything we've told you before, we're violating here because we got it less than 0. So that's what the next theorem finally is saying. The definite integral is an area of a region. If f is continuous and non-negative on a closed interval a to b, then the area of the region bounded by the graph of f, the x-axis and the vertical lines x equal a to x equal b, is this area. If the f is always positive, okay? Like here. That's the one we had way back at the very beginning. Okay? I said at the time, you wouldn't count it down here. You couldn't have the a over here because then it would have incorporated some negative variable. So as long as the f of x is greater than or equal to 0 everywhere between a and b, that's an area. If it's not, you just don't define the definite integral as an area. If it's positive, then you can't. That's all they're saying. They're not saying you can't take the definite integral. It's just no longer an area. As an example of this, consider the region bounded by the graph of f of x equal 4x minus x squared, and the x-axis is shown in this figure. Okay? Because f is continuous, okay, and non-negative on that closed interval from 0 to 4, couldn't include anything out here or over there because then it would have not been non-negative. Then the area is indeed that. And are we going to do that? I'm afraid we are, but maybe not. Maybe they're just showing the area. Let's see. You can evaluate the definite integral in 2 ways. You can use a limit definition, or you can check to see whether the definite integral represents the area of a common geometric region such as a rectangle, triangle, or semicircle. Not any of those, okay? So, I still don't quite figure out why they're doing it this way. Sketch the region corresponding to each definite integral, then evaluate each integral using a geometric formula. They are serious. Let's do the sketch first. How would you sketch that? F of x equal 4. Horizontal. Okay, horizontal line. 4 up. Okay, and you're going from 1 to 3. Okay, from here to here. Ha! I think we can do that. What's the height of that? Mine's not drawing the scale. 4, the width, 2, always positive there, 4 by 2 is 8. Yeah, we can handle that, okay? Riemann sums would give you that, everything would. Okay, this one, x plus 2, when x equals 0, f of x is 2. So 1, 2, 3, 4, 5, 6. I think that'll be enough. Okay. All right. Again, my scale's not really great. You start at 2 here, and you go up a slope of 1, 1, and 1. Okay. So here is the shape there. What is that? Anyone remember what we call that? It's pretty ugly, my drawing, but you get the general idea what that is? Trapezoid, exactly. Remember how we did the area of a trapezoid? Yeah, you just double it, okay? If you take this and flip it over there, you get a rectangle that is 3 this way by, you see, this goes up 1, 2, 3, and this will go up 1, 2, 3 more. Okay, and that would be a rectangle. I knew I was going to run out of room here. 1, 2, 3. Okay. Yeah. This would be a rectangle 1, 2, 3, 4, 5, 6, 7. You add the 2 plus 5, you know, because that is 5 there, 7, okay, and then take half of it. So this would be a 7 by 3, 21 divided by 2, you get 10.5, okay. 21 halves, they call it. That's fine, too. Uh-oh. What do we do about this one? Okay. This is... Oh, no, it's okay. No uh-oh involved here. Thought it would be, but it's not. Okay. Your x is going from -2 to 2. Okay. And what you have here is f of x is equal to the square root of 4 minus x squared, right? What is f of x? In terms of your Cartesian coordinate system. What is f of x? Y. Y value. So this is y. What you can do is square both sides, right? That would give you y squared is equal to 4 minus x squared. And then what does that give you? X squared plus y squared is equal to 4. What do we have there? That is a circle, but it's just a semicircle. 1, 2 high. Yeah, you're absolutely right. That's supposed to be too high. My drawing's not very good. That's not very much of a circle either. But it's a semicircle. Why is it only a semicircle? Because this is only positive, not negative. If that included plus or minus, yeah, that would have been a full circle, but that wouldn't have been a function. This is a function, and that's a semicircle. What's the area of half a circle? What's the area of a circle? Pi r squared. We always thought they were round, but not. So pi r squared over 2, that would be a semicircle, and r is 2 here, so that would be pi times 4 over 2, so this would be 2 pi. Okay. Hopefully they got it right. Yes, that's exactly right. Okay, when possible, do this rather than doing Riemann sums and all those i's and everything else. We're getting closer, but not everything is doable by geometric. These were quite nicely done geometrically. Okay? I didn't write down the first one, did I? 4 by, what was that? 2. 4 by 2 is 8. Okay. And I think that's what we got. Yeah. Okay. Oh, and here it is. They show it here. How are we doing on time? Oh, goodness. This time isn't it? All right, let's just do them quickly. That came out 8. 4 by 2 is 8. Theirs is drawn better to scale than mine. This was a trapezoid, and half of that is you add the major and minor on one, take half of it, and times the width. You got that. And this was half a circle, just like we did the area of a semicircle. All right, we will pick up from there next time. That's the top of page, oh no, here we go. Top of page 275. Let me give you a few homework exercises here before we go. Oh, we made good progress. Do number 3, it's a Calc Chat and Calc View. Any of the odds 5 to 9, they're all a Calc Chat, 7's a Calc View. Do 11, it's a Calc Chat. Any of the odds 13 to 21, they're all a Calc Chat. And any of the odds 23 to 31, they're all at Calc Chat, 25's at Calc View, and we'll pick up the rest of those next time. Yes, and that's it. All right.
We're not meeting Wednesday, right?
Yeah, oh, yes, and let me tell you this too. Sorry, I should have stopped earlier. Y'all say amen, brother. Okay, never mind. Let me get out of this, and let me show you what to do for Wednesday. I think this is what we decided on. Y'all didn't want to meet again. You want to just pick up what I had already covered? Okay. Jake said, yes, yes, yes. Okay. Let me go to Blackboard here if I can and show you what to do. We got into 4.3. Okay. So if I can get Blackboard to open. I'm still recording this, so hopefully people at home will see this as well. I tried it the other way and it was slow. I'm going to see if this is any faster. Okay. There we are. And we'll go down to handouts, PowerPoints, and more. It may actually be faster. Okay. Let's see. Ah, there we go. YouTube videos. Okay. All right. 4.2 to 4, we didn't quite all that covered. So, but starting in this one, I'll leave that one up there. Do that one and this one. The top 2 here. And we'll pick up next time at 4.5. I don't know how far into 4.5 I got last time. I don't think it was super far. We'll just start with 4.5 next time, even though the video will go past that. So finish 4.3 and do 4.4 on the videos, and we'll begin in 4.5. Sound good? All right, good deal. All right. Let me get out of this and get this one saved. Oh, wait, that's not what I want. All right.